In this video, we're going to take a look at the difference between physical and chemical properties and talk a little bit about the difference between physical and chemical changes. This is really a key distinction to make in chemistry since we tend to be less interested in physical properties and more interested in chemical properties, but the different sets of properties can matter in different contexts. And we want to be able to recognize when chemistry is occurring, when chemical change is happening, when chemical properties are relevant, all that good stuff. So let's start by defining exactly what we mean by properties. A property is a characteristic of a substance by which we can identify or describe the substance. And this is almost anything you can think of that we can ascribe to a sample of matter. Mixtures actually have properties as well. This is not necessarily just pure substances. It's things like color, odor, the state of matter, the temperature at which the substance undergoes a phase transition, types of chemical reactivity, rates of chemical reactivity, all kinds of things. Absolutely any way we can describe a substance corresponds to what we call a property. We divide properties into two big buckets related to the way in which we measure the property and what happens to the substance in the course of the measurement or observation of the property. Physical properties are associated with processes or characteristics that don't change the chemical identity of the substance. In other words, they correspond to no change in chemical formula. If the substance isn't changing in its fundamental, say, molecular makeup, we're looking at a physical property. These are things like color and odor, which don't require a chemical change to detect, density, the melting point, the state of matter, the viscosity, how quickly a liquid flows, this kind of thing. These are all physical properties that are just associated with physical changes, right? And the temperatures of phase transitions is commonly where we see this. Things like melting point and boiling point don't require chemical change. The molecular makeup of the substance is the same, right? Ice and liquid water are both H2O. And so that melting point is a physical property. Chemical properties are associated with chemical change and involve characteristics associated with a chemical change, where there's some change in chemical formula of the substance. And we're interested in, say, the rate or extent of that chemical change, whether it happens at all, what happens when a substance undergoes a chemical reaction, things like this. And so chemical properties are things like flammability, how easy is it to combust a material, acidity, toxicity, corrosiveness. All of these properties depend on a chemical reaction to some extent and involve the substance undergoing a chemical change to something else. Corrosiveness, for example, might involve an acid eating through metal. Flammability involves a combustion reaction. Acidity involves the transfer of a proton, things like this. Another way we divide up properties is based on whether they depend on how much of the substance we're looking at or not. And we tend to gravitate towards properties that don't depend on how much of the substance we're looking at, just so we can ascribe the property to the substance itself. It's sort of intrinsic to the substance itself. More on that in a little bit. These two types of properties are called extensive and intensive. Extensive properties do depend on the quantity of the sample, how much we're looking at. These are things like mass, volume, and number of moles that get bigger for bigger samples. So for example, a sample of a solid that weighs 1 gram has a mass of 1 gram. More of that substance might have a mass of 8 grams, and so it's clear that the mass of the sample depends on how much is there. Mass is an extensive property. Intensive properties have the same value regardless of the quantity of the sample, and this makes them intrinsic to the sample itself. Examples of intensive properties involve boiling point, the density, and really any quantity per gram or per mole where we're dividing out the amount of the substance. And so, for example, melting point is another intensive property. For these two samples, say, that weigh 1 gram and 8 grams, as long as we're looking at the same substance chemically, same chemical formula, the melting point will be the same. This sample melts at 82 degrees C, and this sample melts at the same temperature. Melting point is an intensive property. It doesn't depend on how much is there. It only depends in this case on the chemical identity of the substance and what's going on the molecular level involving interactions between the molecules. When it comes to change in chemistry, we distinguish between physical changes and chemical changes. Physical changes might alter the appearance or alter physical properties in general, but do not affect the chemical composition of a substance. Phase transitions, classic example, the melting of wax, a solid to liquid phase transition. Condensing water, water vapor condensing to form liquid water. These are phase transitions that don't change the molecular situation, right? The chemical formulas of everything in these substances remain the same throughout the process, but the physical properties, the state of matter, are, affected during the process. So, phase transitions, physical changes. Chemical changes are chemical reactions, essentially, and chemical reactions alter the chemical structure of the substance. Bonds are broken or formed. Chemical formulas change. Two examples shown on the slide. Iron reacts with oxygen to form rust, and the chemical composition of rust incorporates that oxygen. And so the iron has a different chemical formula after the rusting process. It becomes an iron oxide. And the very act of rusting is a chemical property in and of itself. So chromium metal, for example, is much more resistant to reaction with oxygen than iron is. And so, for example, the rate of reaction of chromium and iron with oxygen is a chemical property associated with this chemical change of reacting with oxygen. Now, in any particular process, physical and chemical changes may both occur, and this is actually very common. For example, we might need to heat a chemical reaction to get it going, and maybe that causes some evaporation of a liquid into the gaseous state. At the same time, bonds are being broken and formed and a chemical change is occurring. An example closer to everyday life is frying an egg. There's a solid to liquid phase transition that takes place. This is a physical change since no bonds are being made and broken to go from a liquid to a solid. The molecules are just changing how they're arranged. But at the same time, browning takes place, and browning is a chemical change. The chemical makeup of the brown bits of the fried egg are different from the chemical makeup of the liquid white and yolk that we started with. So this is a chemical change. And while that might be difficult to verify visually, chemical analysis of the different components of the egg before and after the frying process would verify that, yes, a chemical change took place. In general, though, there are cases where physical and chemical change and the distinction between these two is a little bit murky. One example is the dissolution of an ionic salt in water. So solid sodium chloride, for example, looks like this picture on the left with cations and anions, positive and negatively charged ions, sitting next to each other in a nicely ordered lattice. When you take that and you dissolve it in water, water molecules, which you see here in red and white, surround the cations and anions, surround the ions and cause them to separate from each other. So in a sense, where there is attraction between the ions in the solid state, they get separated in the solution once they're dissolved. And so we might infer from that that an ionic bond has been broken. But that's sort of debatable whether the ionic bond is a bond in the first place. And so this was one example where whether this was a chemical or physical change was actually debated back in the day. We don't worry about such debates too much nowadays, but it is, I think, worth keeping in mind that this distinction between physical and chemical change can be a little bit murky in some cases.